Welcome to the afternoon session. I hope everybody had a good lunch. And so today we're going to have 3 panel discussions in the afternoon. Then we'll have there's a poster reception. And our first panel discussion is focused on methods and algorithms. And the focus here is really on the theoretical foundations of scientific computing, the analysis and the algorithms that enable everything that we do here at the Institute. And that really have formed a key part of the intellectual core of the Institute throughout the various incarnations over 50 years here. And the format of the panel will be, I will start by having a discussion with the panelists for maybe 20, 25 minutes, and then we'll open up for questions from the audience. We have an overflow row. I'm not sure if it's used, but we may have remote questions coming in as well. I think I will start with asking the panelists to introduce themselves, like where you're from, and also if you want to tell us, what do you enjoy most about your work? So, please.
Okay, so my name is Björn Enquist, and I am affiliated with mathematics apart from the Oden Institute. So I do computational methods, or naturally in that. Started off in differential equations, right now doing optimization.
And what do you enjoy about your work?
Everything. I enjoy teaching, above all, of course, I do sitting on my own and do my research.
Yeah. Beatrice.
My name is Beatrice Rivière. I'm a Noah Harding Chair and Professor in the Department of Computational Applied Mathematics and Operation Research at Rice. I know the name of the department is a mouthful, but okay. I'm here because I'm very happy to be here and honored to be part of the celebration of the 50th anniversary. And I think I'm here because I'm a product of the Oden Institute. So I graduated in 2000 under the supervision of Professor Mary Wheeler. And I have very fond memories of my time at the Oden Institute. At that time, it was TICAM, and we talk about the Taylor building. And then there's also 1 year in the old campus hospital that was interesting. And then we moved into this wonderful POB building. I worked on numerical methods for partial differential equations in application in geosciences, particularly subsurface, but also in biomedicine. So working with MDs and PhDs in the Texas Medical Center on blood flow modeling or modeling of drug delivery and so on. So more recently, over the last 5-6 years, I've been working in machine learning. And that I mention this because I work in collaboration with another graduate of the Oden Institute, Professor David Fuentes, who is a faculty at MD Anderson. So we developed new architecture for neural network for doing medical imaging. So I really think this Oden Institute is a wonderful place. I felt like when I was a student and a postdoc, I could just learn just by breathing the air, right? Learn by osmosis. It's a very rich environment of research, and I'm very happy to be affiliated with it.
Yeah, I'm Alex Dimakis. I'm a professor in the Electrical and Computer Engineering department here in UT. I work on generative models and deep learning. I'm specifically applications in imaging, some applications in medical imaging, and also text generative models now. What I enjoy most about my work, okay, so I guess I don't know if I enjoy it, but what's happening in my field right now is that every month or so you have something that appears that you're like, whoa, I didn't think that was even possible. So there's actually an incredible pace of progress, which is exciting, but also extremely kind of challenging and stressful to keep up with, and for our students and for us to kind of stay on top of what's happening. So I enjoy it, but not all the time.
George.
So I'm George Biros. I'm a faculty here at Oden, and I have appointments also mechanical engineering, a secondary in computer science. I work in the interface between high-performance computing applications and computational mathematics. I think too many different types of problems, actually. But what I enjoy most, I think, small group interactions with either colleagues or students, trying to brainstorm, and also occasionally teaching when there's a beautiful results and I show to the students. It's kind of exciting.
Thank you. And I hope the focus, or I will make sure that the focus of this panel will be mostly forwards-looking, but it is a semi-centenary celebration, so I think we should start with taking a little bit of a retrospective. So I'll follow up on the question from this morning. Like, what are the major developments in the field in the past 50 years? Like, what do you consider to be the main things that have really moved the field forwards within methods and algorithms? Björn, you want to start?
Okay. Yeah, I think the main driving force has certainly been the evolution of the computer. I mean, that is made it possible to do things of applied nature. So the secondary thing and the effect out of that is, of course, that so much broader field can be handled by computational science and engineering than could be done in the beginning. And then on the analysis side, that I would say there's two branches that work together, and one is the development of methods that can be applied in the real world, and analysis of these methods. And there are different things where the analysis helps the applications or the methods, and methods trigger analysis. The type of work that was done over here, mainly then during the TICOM area, was a development of the finite element method as a practical tool. And that's a good example where there was work done in the labs, Boeing, etc., on the practical side, and then bouncing back to mathematics. It started over in the math side as an abstract tool, and then coming back, understanding what can be done and not, and thereby being able to apply it in a wide variety where the Boeing engineer were not thinking of.
Yes, so I think I will touch upon a couple of things that were already discussed this morning, especially in the talk by Doug. So I think for me, high-order methods has been a great advance. So the high-orders method have been shown to be accurate and robust for solving linear or nonlinear problems for which the exact solution may not be smooth. Another advance is this flexible methods, in particular method that can handle general hybrid matches. So I'm thinking in particular in the class of polytopic methods. And then to talk about the advances in the computing world, accelerators, I think the GPUs has really changed the landscape. And now when we develop algorithms, we really have to think how they are better implemented on these GPUs or this hybrid architecture so that we get scalability.
Yeah, so I think in machine learning, many of us, we're working on problems that are principled, like, I was working on sparse PCA, provable approximation algorithms for sparse pre-span components and so on. Combinatorial optimization, it was all great. And then I remember we went to NeurIPS, and there's these deep learning guys, and we were like, oh, they're hackers, there's some, we probably don't believe it. This was real, like most of us didn't believe in this deep learning thing. It was like, okay, neural nets, they're supposed to be solving a non-convex problem, who knows, they'll probably get stuck in some bad local minimum. The story that I heard afterwards is that Jeff Hinton called Jitendra Malik at Berkeley, said, okay, why don't you like deep learning? What do you want me to do so that you take deep learning seriously? He said, beat Pascal. There was a Pascal challenge. He said, okay, I can't beat Pascal. There's not enough data. What about ImageNet? If I beat state-of-the-art on ImageNet, will you take it seriously? He said, okay. And then the story is that I think they did this AlexNet thing. I don't remember, 11 or 12. And they actually crushed ImageNet. And everybody said, okay, I have to stop what I'm doing. And I have to start doing deep learning. And that has completely, I mean, I literally stopped. I was interested more in unsupervised methods because I'm like, okay, supervised works. Let's not try to jump on that train. Then in unsupervised learning, GANs came out. DC GAN came out in 17 or 16. I saw the faces. And like, I cannot believe these are created by a neural network, maybe just memorized. Then I tried to produce my own face. The moment I started producing faces of people that I knew were not in the training set, I'm like, okay, there's something incredible happening here. So in unsupervised learning specifically now, diffusions, stochastic differential equations, diffusions is incredibly exciting. So it keeps happening that it's driven by the data and the compute, and very simple algorithms. First order, SGD, very simple things scaled to the extreme, I think.
George?
So, I mean, 50 years before, the word didn't exist for me, so everything is a huge advance. But I think first finite element methods and the impact that had in industry, from car simulations to aerospace, they have a tremendous economic impact. I think also atomistic calculations, a combination of n-body methods that enable molecular dynamics, it was a huge advance and had, again, significant impact. I mean, where do I stop? Optimization methods, and especially data simulation, if we're looking at economic impact in terms of energy resource management or weather prediction, combination of forward modeling, inverse modeling, statistics, these are tremendous advances that have a societal impact. More technically, the advances in solvers, linear and nonlinear, David mentioned, your slides had basically starting from NVIDIA machine, but going to COCOS and then PIC codes and finite element codes and atomistic. So there are, and also let's not forget discrete algorithms like graphs and sorting and mesh partitioning, basically contributions for theoretical computer science that helped put a lot of these technologies together. So, I mean, everything really has changed the last 50 years, and from level set methods to finite element to integral equations, there are just too many to mention, I think. And a randomized method also. You know.
So for my next question, I think I'll set aside Alex, because your answer is going to be obvious. But for the rest of you, is there something that's happened that was very unexpected to you? Like, some of these things have been sort of a steady progression from where we were, or where people were 50 years ago, and sort of it's continued as one would expect. Something that surprised you in your careers?
I think many things are evolutionary. I had sort of my first student in deep learning, or maybe I should say shallow learning, and that was in 1990. And that was to map that. And then, of course, there had been a gradual advance, and even started before that, of course, on the theoretical level. So I wouldn't say that was a surprise. There was a surprise of the efficiency that happened during the last decade when it comes to machine learning. And there are other things also there that are gradual. It is not like FFT. It came overnight and then changed everything. The finite element method, finite difference method took decades in order to be efficient. So it's not, what could come as a surprise and a paradigm shift would be quantum computing. And also there is a history. I was on a Nevanlinna committee 98, I think, so it's a quarter of a century ago when Peter Shor got the Nevanlinna Prize for quantum computing algorithms. And at that time, there were a couple of qubits running in a lab, and the projection was that in 10 years it would be a commercial product. Now there are a bit more qubits running in the lab, and projection is that in 10 years there will be a commercial product. So I'm waiting for that.
Yeah. Beatrice, George, any surprises?
Well, I agree with the quantum computing. I'm also waiting for it to materialize, even though there's more and more machines available for people to actually start playing with them. But for me, as an educator, I'm always surprised when I see any undergraduate student putting up the laptop and starting to do GPU computing just by getting access to Colab or AWS, and with a small monetary fee. So for me, it has changed the way I teach and train the student, because I know these are small computing capabilities, but so easily accessible, they can try an algorithm and test ideas.
I have answered the question already.
I think the interesting results in high-dimensional problems, I don't know if it's a surprise, almost like the beauty of it. It's surprising for example, in n-body methods that have some work, the kind of the integration of geometry, algebra, analysis, and actually discrete algorithms to come up with the solutions is kind of surprisingly beautiful, at least for me. Advances like compressed sensing and wavelets that are a little bit unexpected, and they're very also beautiful results. I think this, in deep learning, the composition of functions as a way to approximate complex functions is a little bit surprising that it's so effective. And also, I think the people that worked in these fields, the creation of open source software that has such a huge impact, and basically people volunteer the time and create technology. So that's also a little bit surprising that people did that and has significant impact.
So let's move the focus. We already started a little bit with quantum computing, but going forward, where do we expect to see, what are the major developments in the next, say, 10, 20 years going to be? And we'll start from the right this time, George.
Quantum computing, I don't know anything about quantum computing. I think it's a physics problem now, and when it's solved, it's going to be exciting. But also, I think from basic principles, it requires problems that have order 1 input and order 1 output. So for these problems, it will have probably significant impact. But if the input is order n, there are interesting questions on how it can help. But I think it's exciting. It's just I'm very far from it, so I cannot really.
So in other areas beside quantum, like, where
quantum,
do you
I think analog computing will be very interesting to see what can happen there. I think there's a lot of emphasis on getting things faster, but it will be something to see in photonics. This is, again, technologies to accelerate really data movement. With respect to algorithms, I think it's very random. I don't know. I think we're going to, the analysis now, the exciting things, of course, is the scientific machine learning, how you work with data, but also how you come up with the guarantees that were used in scientific computing. You can say, I want 5 digits, 7 digits, 8 digits of accuracy, and I can guarantee to get it, as opposed to once in a, maybe it will happen, maybe not. So, but I cannot really comment on other topics. Maybe Alex.
The things I think are exciting, I mean, there's obviously many exciting things that I cannot say anything intelligent about, like quantum, I don't know anything about. But I think in the generative AI space, there's a huge opportunity / risk right now that many jobs are actually not requiring that much intelligence. They can be automated, and they will be automated. So there's going to be a huge, disruption in many markets. Self-driving cars are, as you know, driving around. So there's also a lot of disruption that's happening there. I think the problems and the research that is exciting in this space is, grounding to existing documents, so you reduce hallucinations, the alignment problems, the problems of being able to, you upload all the papers published in all the journals, and you can actually talk to all the papers and ask, is there a paper that did this? And you have like GPT type of functionality, but with retrieval. I think that's an incredibly valuable tool, and there's countless uses where if you actually make it into a retrieval problem grounded on a database, I can see countless uses of that in a group of documents, in a database, in a group of legal documents, in a group of medical documents, countless applications. Multimodal is very hot right now, and I think will have a lot of impact, where you can also have images. So you can do super resolution, deblurring, but also have an interaction with language. Like DALL-E 3 came out yesterday, and it's doing that. You're actually able to generate an image and say, add another tree to the right, make it more look like this cinematic director. So you're literally interacting with a generated image in an extremely interesting way. So I think this is a space where there's going to be a lot of excitement in my field.
Okay, so I wanted to say a few more words about machine learning. I know machine learning has been quite popular these days, but the reality is that when you use machine learning, especially thinking of deep learning algorithm, the results are only as good as your training data. And that's where the problem is, because the training data may have a lot of bias in it, may not be fair. So I think what people should be working on is trying to build this safeguard so that the machine learning algorithms are reliable, fair, and give you a good idea of the solution of the problem without any biases. And I'm very excited about a possibility to do that is to combine the physics models with the data-based models. So what I call scientific machine learning, and that's a term that other people have used, are using in the field. So this is quite hot, where we are trying to do the typical functional analysis, approximation theory, finite element error analysis. We combine that with these, the optimization and the trying to understand this Adam optimizer in the neural network. So there's a lot of papers already over the last 2-3 years. I'm working with a student and a postdoc on a particular method, and I think this is, I'm expecting in the next 5 years there will be a lot more work coming out of that.
Okay, so I'll do some on the analysis side again, coming from the math thing. And I think we have the classical computational science pipeline. You have the process, let's say, airflow around an airplane, growth of a tumor, effect of hurricanes, or whatever it is. And then we make a mathematical model. We have to have a quantity model in order to do something like that, traditional thing. Then we take the next step. We discretize that, and we have a solver for that. After that, we have a code that fits to a good computing architecture. We add data, and we get the result. This is a nice flow pipeline that we have. And we have good analysis for each individual part. Things become a little bit more complicated these days. And what we would need is an analysis that look on a little higher level and be able to guide. For example, the model may not come from physics directly. It could, for example, come from computation. We do snapshots. We get a reduced order model that then is used inside the computation. Data may be needed in order to get the model, data-driven models. Data could come during the calculation, data assimilation, which is needed in weather forecasting, digital twins, etc. And I would like to see analysis raised so we can do that on the more complex setting. A good example is actually for the need of that is deep learning. So we have good theory, if I know scientific application I'm thinking about here, of approximation, the universal approximation theorem, that it's possible to approximate a function. And then we have quite good understanding of stochastic gradient descent, that you can actually minimize sort of the loss function with rigor. We have absolutely no understanding if we combine these two. There is no error estimate, there is no convergence result, there is nothing of that. Nobody else could get through with this in sort of the regular computational science setting. It would be nice to have a rigorous estimate on generalization error in sort of the scientific setting.
Right, so I'll open up for discussions, for questions from the audience in a moment, but I have one last question, which is, what do you view going forward? So what's your thinking about, as educators, what are the key skills we need to teach the students? That when the Institute started, it was fairly straightforward. The focus was on computational mechanics, solving PDEs. We need to do functional analysis. We need a bit of linear algebra to solve the resulting linear systems. Now the scope of the Institute has broadened. Things are evolving. We're using other types of techniques. So what are the foundational science parts, the foundational parts of math and computer science and whatever it is? What should young people learn? George?
I mean, already the schedule is pretty packed, so I cannot start removing. But I think perhaps I will say that perhaps the computational science engineering, there was a question at some point whether it has a place as an undergraduate topic, but I think it becomes appear that the different topics from probability theory, computational statistics, machine learning, linear algebra, nonlinear optimization, convex analysis, blah, blah, all these perhaps they are necessary tools that one can appreciate the complexity of data and applications, but perhaps one has to start earlier. And that's my comment. And I think already here at UT we have this this activity at aerospace, but I think it has to be broader and nationwide, have more programs that are focused in this kind of topic. But I know this is very controversial.
Alex?
Yeah, so in the Intro to Data Science class I'm teaching, it's basically an introduction to machine learning in the ECE department. There's two parts. There is the, essentially I end up teaching probability and linear algebra. That's the part that I have a hard time, and I think that's like super foundational for everything in my space. And then in addition to that, of course, there is the PyTorch, the modern software stack that I think is incredibly important for the students to be able to actually play with a modern tool. So we try to teach both, and I think that it's extremely empowering for the students to learn PyTorch and be able to try a new idea. It's so fast and easy once you have become fluent in this technical tool to try mathematical ideas, new algorithms, and so on. But the foundations, I think, probability, linear algebra, stochastic differential equations, as I said, is actually very important right now in generative modeling. Yeah, I think emphasizing more the computing, the PyTorch part is what I'm seeing as important. And the students are very good at that. They're actually much better than I am in picking it up. But they do need they need an ecosystem, and they also need actually compute. That's another thing. And I see Dan here, who's really the foundation for us to have TAC. Like when I want to teach PyTorch, they have to have GPUs. If they don't have GPUs, we cannot teach it. It's like trying to teach computing without computers, you know? So we really need more of that. And it's not any computer. It's only NVIDIA GPUs. There's a monopoly. It has been going on forever. And you know, the monopoly remains because of the middleware reasons. I'll be glad to talk about it.
We're being recorded.
What's that? No. I'm on the NVIDIA advisory board, right? I mean, I'm telling them. No, there is a monopoly. The reason the monopoly is there is because of CUDA. There's a middleware. Everybody makes very good chips, but then they don't talk to PyTorch. So they can do matrix multiplies, but they're not actually, you can't just import Llama and play with it because of the software. There's a thin software bottleneck somewhere. So but right now for us, we do need access to GPUs, and we do need to train the kids in PyTorch. I really think about that.
Beatrice.
Yeah, so I think this is a tough question. So research, even within the field of computational applied math, is becoming more and more, interdisciplinary, in the sense that mixing different types of subject together, and there's only so much time that you have as a graduate student. And usually you want to dedicate maybe 2 years taking courses and then 2 or 3 years doing purely research. So I know in my department, we do try not to, we make sure that the students take a series of 2 courses where they learn about programming. So they do learn about GPUs and CPUs and MPIs in a course. It's a required course. And then after that, we have numerical analysis, a little bit of finite element method, a little bit of stochastic statistics course, linear algebra, and then after that, the advisor will kind of, each advisor will have their own view of what courses they need to take. But I always tell at least my group that even though you're done with your required courses, take as many courses as you can, because that is the best time in your career where you actually can absorb a lot of new material.
Yeah, if I look at the current curriculum over here, I think of the basic things that would be needed is probability and statistics for UQ, and of course many models these days do that, need that overall. I think there are other things that one would like to add into this. The hard thing is what to take out. Because everything is sort of needed of what already exists. I do that. I think it is good to have something close to software engineering, which we don't have directly. I still think there should be a rigorous mathematical part. We need Todd as gatekeeper over here, so that should continue. Well, it could change focus in this part.
We have just over 10 minutes left, and I'm sure the panelists will be happy to take questions from the audience. Leszek.
I have more or less Proud is about learning more and more. I mean, that was always his philosophy. And I think this is more and more true, that if you work in such an interdisciplinary field like ours, you really have to put up more work than, if you're just a single field guy. I wanted to touch upon a different subject, right? I mean, we give a lot of lip service to mathematics, but at the same time, we are taking away from the curriculum already hard function analysis, linear function analysis, right? And we completely forgot about nonlinear function analysis, which was very popular and taught by Tinsley himself, subject in the 80s, right? And the difference between linear and nonlinear is huge because, we just celebrated 100th anniversary of Bannach's dissertation. We have a pretty much complete theory for linear problems, but each nonlinear problem is coming with its own theory. And all we can do in computations, right, where stability is needed, is reproduce the stability of the continuous problem, in some way mimic it. It's the only one way we know how to proceed to solve them. Yeah, we have classes of point conservation laws, semi-monotone operators, blah, 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 where there's some commonality. But if it comes to challenging problems, you really have to understand the mathematical structure of the nonlinear problem. And that one is missing for me right now in our curriculum. We are teaching less and less classes about that. When we offer them, nobody wants to take them because now they're hot subject, right? Well, I want to teach them. So this is something that I believe we should be very careful about completely dropping out because it will be very, very difficult to come back.
Any other comments, questions? Clint, up front here.
So we heard a lot about linear algebra today. Why do students struggle so much with linear algebra? I hear over and over from my professors in my department that the students don't know linear algebra. It seems like we teach them, they learn linear algebra in
Not me?
No, anybody. I'm looking at you. I'm looking at you because
it's your fault.
I'm looking at you because you teach the linear algebra course for one thing.
I think
And I just like to look at you. I don't know.
I think the problem with linear algebra is it's needed everywhere. The moment you touch a computer, you have to know linear algebra. And people don't want to do mathematics. A lot of people that want to do computers and they want to work on ChatGPT, they don't want to do mathematics. And so it doesn't come, that's people, and it's needed everywhere. And a lot of people take it like 1 year. I hated the linear algebra as an undergraduate. It was only when I did fluid mechanics and that I realized, oh, that's useful, or vibrations. I said, I can AX equals lambda x. Who cares? And then I did vibrations, and then I realized what's going on. So I think a lot of problem for non-mathematicians is that they don't really appreciate how ubiquitous it is. I think that's my explanation, at least. I don't know.
It's also really hard. I mean, just my sense. Also, I didn't get it in my undergraduate. I actually got a graduate PhD level, then I actually was working on these problems, and I think I actually started understanding the depth of linear algebra much after our students are faced with it. And it's actually very, like probability. You can just basically, or statistics, you can just dive infinitely deep, I think, and they're also extremely useful in so many disciplines. I don't think it's an easy thing to teach here.
I think it's a marketing issue, like some students, they say, oh, linear algebra, what do we do with that, right? So I taught linear algebra recently for graduate students, and I revamped the course. I took, papers by Gunnar and tried to, so motivate them and talk about multigrid and so on, and throw some neural network, show the connection between data science and multigrid. There's a real connection, especially for the unit, and try to motivate the students. So otherwise, they don't really understand why it's important.
Well, I'm an aberration here. I had too much linear algebra in my
Any other?
Sorry?
Can you still prove the price?
If I get some time, yes, I could do that. It's a nice circular proof in a way. Right.
Other questions, comments? I'll ask one then about going forwards. So, of course, thinking about going forwards, everybody's thinking about quantum and AI and machine learning. What's something we're not talking about? Are there any bubblers? Something that could move things.
I mean, a lot of problems remain unsolved, and we just move on. I think the long time horizon simulations are outside the data science. It's an open problem in many disciplines, and we still don't think generically. We don't know how to deal with that, but that's not very exciting, I think, for most people, kind of boring, but I think that's a very important open problem. I don't know about. It's hard to predict surprises.
I think one thing is development of software that helps out in not only application, but listening to David this morning about the details in how you move around on a chip, the data. If that can be handled with software and hidden, at least hidden from me, then that would be a good help. Yeah. Yeah.
What about the great unsolved problem, high-frequency helmets?
Yeah, right, right.
We can hope.
When are we going to get a breakthrough on that?
Actually, it was a question that was asked this morning, and it's sort of relevant to this notion of unsolved problems. Methods and algorithms, like you've all articulated beautifully, sit under everything that has been achieved in computational science and engineering. Good luck selling that to Congress. And I think it would be great to hear some of your thoughts on what should, particularly the math community, but the math and then sort of, the people like me who are not real mathematicians, sort of the neighboring communities. What do we do beyond just machine learning? Machine learning has helped in sort of selling some of that, but for these important unsolved problems that still need math and algorithmic development, how do we convince non-experts in society at large that it's still worth investment? This is a very easy question to.
Good. I mean, one thing, since you mentioned that yesterday there was in the Senate, they had showcasing of the AI institutes, and I was attending, and one of the things I realized that shocked me, you said it's easy for machine learning and AI, but I realized that the general public, when they think about AI, they think of, Elon, and they think of, Sam Altman, so they think of the companies. They don't actually think of the universities as contributing anything in research, in deep learning. So one of the things that I was saying, and I think many of us can say, is that the algorithms, the linear algebra, the fundamentals, the SVD, like the very fundamental things that are powering the AI revolution were primarily invented in universities. It's not that, okay, there is, a kid in OpenAI hacked the latest version of DALL-E 3 and launched it, and that has become viral, and everybody knows about that, which is great. And I'm not saying it's easy, but the fundamentals, the algorithms, the architectures are all relying on mathematical innovations that are primarily done in academia, and I think the general public doesn't know that. So even for things that they do know, even for things that they do use like transformers, everybody knows, oh, transformer was invented at Google by XYZ, but they don't know that the transformer was built on self-attention, which was invented by Bengio and many others, right? So in a university setting. So I think the universities are not getting a fair share, even in the easiest of the cases that you said. In the other cases, I don't know. I mean, I guess just advocating, reaching out.
I think David answered this morning. We have to. It's a very difficult challenge. We have to tag along with application people, or talk to agencies that have a better understanding. DOE has been fantastic in supporting our community, and perhaps partner and try to have an insider But David, I think you said you have to tag along with application people and make the case.
Slip under their headlines.
Yes.
Slip under the headline and then emphasize that in order to execute these things, you see the pretty pictures, you see the results of these big machine learning models, and breaking down that the flops that are actually executed there, it all relies on these algorithms.
Or find the industry leaders that appreciate this and then use them as a voice. Because us, they're not.
Well, I think we also have to keep pushing the importance of fundamental research. We can't lose that. We keep emphasizing fundamental research. There are methods that have been sitting around for 100 years that may prove to be useful 50 years from now when quantum computing finally comes. David was mentioning to me yesterday, he's hosting the Domain Decomposition Conference in January at KAUST, which has been running for 30 years now, I think it is. And these are based on methods from the 1800s, Schwartz and so on, that found suddenly new life when parallel computing came along, and you had to decompose a problem into sub-problems that you would then have to intelligently combine together. So we lose sight of these things when we focus on the applications, of course, are very important, and they help justify the public, these investments, but we can't lose sight of the fundamental research. We have to keep stressing to the funding agencies that if you're not investing in fundamental research today, which is the engine that will power advances in 50 years from now, what are you going to do when 50 years comes and you don't have those, the multi-grid from the Fedorenko, 1960s or whatever it was.
Last comment, David.
Just a favorite, actually, it's a favorite example to riff off of what Omar said, is space filling curves. One of the most obscure mathematical curiosities, Hilbert, in the 1890s, and now we use it to lay out multidimensional problems in linear memory space, to keep things that are near each other in high-dimensional space near each other. Maybe it's the uttermost purely useless idea ever, right? Until computers came. Right?
And then John Salmon came.
Just another example from Omar's plea for more fundamental.
Examples from history, there is what can sell both for deep things like finding gravity waves to getting vaccines or helping out in everyday life.
All right, the discussion is great, but I don't want to eat too much into the next panel's time. So maybe we should wrap up at this point. So let us thank the panelists very much.